Thanks for the introduction. Yep, so I'm Evan. Very excited to be able to present my work here. I've been working between two labs, a computer engineering lab and a physics lab, and we have a really interesting project where we can marry the ideas from experimental quantum computing and ideas borrowed from classical compiler research in order to kind of get the best of both worlds. And I'll introduce this methodology of co-design, which is the main principles guiding our research, and will guide a lot of the ideas of this talk. So I'd like to start by saying that the field of quantum computing, which is only existed for a little over 40 years, for a long time, the research was very independent between the applied mathematicians like Shor and Grover developing their algorithms and the efforts from the experimentalists who were just trying to design qubits that were long enough lived to eventually build a large enough quantum computer. And until very recently, our systems became sophisticated enough where the idea of actually running algorithms on our quantum computers became possible with experiments like Google's quantum supremacy experiments and a lot of the new efforts from IBM scaling to 1,000 qubits. And because we're in this stage of NISQ, it leads us to ask if we might use information from quantum algorithms to redirect some of our physical design choices. Are there things that we might do to build a quantum computer differently so that it's more well-suited for actually running algorithms? And that's one of the main ideas of co-design. And there's two main separations of concerns that guide this. The first is this leg on the left, which deals with our physical devices have limited qubit connectivity. This means that we can't perform our gates between arbitrary pairs of qubits. Just the physical mechanisms which create the qubits and create the couplings between them, which we'll refer to as a modulator, just some generic creation of couplings between qubits, means that we can't talk to all qubits to one another. This comes to ideas of like frequency crowding. In order to address this, we have placement and routing algorithms that use swap gates to perform data movement. But because these swaps are so expensive, this becomes a really important concern in order to optimize, so we don't spend our entire time having our qubits decay while just trying to do data movement. And the leg on the right deals with the basis gates. Characterizing and calibrating a single basis gate is a fairly involved process. And depending on how we've built our quantum device, we only have access to a certain set of basis gates that we can calibrate. So different devices like IBM, they have the cross-resonance gates, or from Google, they have their FSIM gate, which is the ISWAP with some ZZ interactions. And depending on what we've been able to calibrate, we'd hopefully be able to calibrate something high fidelity, but it means that we have to translate all of our algorithms into circuits only comprised of this gate. And so we need to choose some sort of physical device that enables us to have a basis gate that can efficiently do this decomposition. So instead of having a purely separated stack of concerns, the co-design identifies that a lot of these are intermingled. So for example, the bottom stack directly influences what sorts of topologies and hardware gates are possible. If I've created a quantum computer in a particular type of superconducting chip or with a trapped ion device or so on, naturally, the different types of topologies or gates will appear. For example, in trapped ions, we might have a more natural mechanism for all-to-all topology than in a superconducting device where I need physical coupling capacitors between my qubits. But we also have these arrows pointing down from placement and the topologies and translation to the hardware gates, where I might use the knowledge of my device to redesign my transpilation stack, these two main algorithms. For example, I could design a routing algorithm with a certain topology in mind, or I could try to design a translation algorithm or decomposition with a particular hardware mechanism in mind, like the specific interaction that might optimize. And this is where our research has been and I'll try to introduce our research through topologies, through optimizing basis gates, and then most recently, sort of a mingling of the ideas of basis translation and routing at the same time. So our first project that I did with this lab was the idea of the qubit connectivities. The first thing we recognized is that in the industry, there had been a growing trend to have our topologies become less and less connected. So IBM, in order to make their gate fidelities higher, understandably, they made the qubit connectivities less connected in order to have more uniquely address the pairs of interactions on their topologies. if there's less qubits connected to one another, they're going to have higher fidelity interactions. And so rather than having something like a square lattice, they've been moving towards a heavy hex topology. But this made us question whether or not this was a harmful design trend, because although we have higher fidelity gates, we have less connectivity and require more swap gates, which ultimately could be a different killer for our fidelity of our circuits. So the research idea was to study different topologies and then see how efficiently circuits could map to those topologies and analyze how much time they would lose to just doing data movement. And the co-design was to take the type of modulator from our experimentalists and see if we could design a topology that was physically possible and would have less constraint data movement costs. So the sort of obvious idea was the tree, because of the modulator. The snail has a local Alt-Hall neighborhood, and you can kind of just piece these together and stitch together local Alt-Hall neighborhoods and build a tree. But because of their building a natural bottleneck in the middle, what we realized is we could build something different, which is this picture of the corral. So what we were given was a snail that had a restriction of 4 qubits could connect to one snail, and all of the qubits connected to one snail would create a topology. And so the co-design and CS understanding of classical networks, kind of inspired by what ended up being a hypercube, led us to build the corral and build this very efficient topology. And what we learned from using the Qiskit transpiler, just mapping circuits to these topologies, is that unsurprisingly, the blue and the green lines here, let me pull up a laser pointer, from the heavy hex and the square lattice scale much less favorably than the purple and pink lines, the corrals. And this is only for small examples. Up to only 16 qubits, we can start seeing there's a large gap already being built just from having more densely connected topologies. So we identified this as a very important point of concern that experimentalists should be concerned with. So after this, setting aside topologies, we started examining what sorts of basis gates would be possible. And this is sort of a question like designing a classical ISA. If we can calibrate a single instruction, since it's such a lengthy and difficult process, what would be that best instruction we could calibrate? So what does it mean to use an instruction or to use a gate to decompose algorithms? And the picture kind of looks like this, where for every 2-qubit gate in the circuit that you hand me, my transpiler, I would decompose it into sequences of my 2-qubit basis gate. And I would have to just play my 2-qubit basis gate enough sufficient times so this decomposition is possible. And by that, I mean there exists a solution to the single qubit interleaving gates to make the decomposition. This means that our concern for choosing a best basis gate should be one that most efficiently reduces this time of decomposition. And you can do that with 2 ways. Either you have a 2-qubit basis gate that is itself a very fast gate. So if I play it multiple times, the overall duration is very short. Or I have a very efficient decomposer, meaning that to decompose an arbitrary target, I, on average, don't need many applications of that basis gate. And so we're working to balance those 2 concerns and overall reduce the duration or overall improve the fidelity of our circuits. So we need some sort of way to analyze our hardware and characterize which basis gate would do that. And the way we end up using, approaching this problem is we use this theory of the wild chamber, which is a concept borrowed from Lie algebra. And this is a representation of 2-qubit gates that map to this geometric space. And it removes, importantly, local variances. And so each coordinate is just the local invariance of a gate, which means practically the single qubit gates that are before and after 2-qubit gate are taken away when we create the coordinate of a gate. So for example, you might know the CZ and the CX gate differ by Hadamard gates. And so both CZ and ZX map to this coordinate here. And so this is very useful, and you're going to see this picture appear in most of the other slides of this talk. And I use it constantly in my research because it's very helpful for us visualizing what gates are doing and how gates are related to one another. So I'll also just point out some of the key points. We have ISWAP on this far corner. The top corner is the swap. These 2 base corners are the identity. And this point between identity and ISWAP is the square root of ISWAP. Something we did was we took a set of NISQ algorithms, things that we could actually run, again, relating back to this idea of co-design, and we visualized where gates from circuits that we know appear in the wall chamber. And what we found is that the CNOT gate appears pretty ubiquitously. And this is not surprising because the CNOT gate is how we can like classically understand circuits and how we can create notions of like pretty much all of the building blocks of circuits we know, like controlled phase gates and controlled unitaries building parity measurements and Shores and Grovers. They all use CNOT gates. And the second most appearing gate was the swap gate. And this was also unsurprising because we knew data movement would be so important. And we have some C-phase gates, for example, from the QFT, and some other stray gates that we'll discuss why these appear later. So again, to say the goal is we're going to use these to determine for some quantum computer what basis gate they should calibrate, what's something that decomposes circuits efficiently and something that is could be fast on their hardware. So the first part to answer this question is to understand for some hardware, which in our case our collaborators use a snail-based quantum module, what types of basis gates can they build? And so this is kind of the landscape of candidate basis gates. The snail is a superconducting nonlinear asymmetric inductive element. I'm not going to go into a lot of details for how this works, but I'll direct you to my collaborators, Minkong and Chao's recent work that describes the specific engineering of the snail in detail. But for our concerns, we know that the snail creates gates in our systems by driving the snail at either the frequency difference of its coupled qubits, which creates this conversion interaction term over Hamiltonian, or driving the snail at the frequency sum of the two qubits in the system, which creates this gain. So this Hamiltonian is the design space where the different parametrizations of the two driving terms of conversion and gain would be what creates our unitary. And if we map this back to the Weil chamber, we get some plot here, and we can see that different ratios between conversion and gain create the different gates. So for example, the most natural choice that falls out is just having only conversion or only gain, which gives us this I-swap. And it's an I-swap continuum because these gates are all continuous in time. So if I start with no interaction at identity and I drive over time, I move on this vector towards I-swap. If I drive at a 3-to-1 ratio, I get a B. And if I drive at a 1-to-1 ratio, I get a C-naught. And we know that the harder we drive these terms, the faster they will be. So the other important thing for us to realize was that there's an inverse relationship between the amplitude or like the rate of driving and the time. So basically, if I work harder, I'll finish faster. So again, there's two parts to this question, the decomposition efficiency and the hardware speed. And the first part I'll talk about now is the decomposition efficiency. So to reason about for a particular basis gate, just the landscape that I showed the previous spot, for each of these gates, which one is the most efficient at decomposing gates of our circuit? And to understand this, we'll use this theory of monodromy polytopes, which is a very powerful tool for reasoning about the decomposition power, and most crucially, without actually having to do the decompositions. Instead, we get these polytopes that appear in the Weil chamber as regions of accessible gates for some number of applications of the basis gate. So here I'm showing you the I-swap gate, and with only one I-swap, I can only ever build the I-swap. Hence, this is just a single point in the space. For two I-swaps, I can build any gate on the bottom plane, so anything inside of this green region. And for three I-swaps, I could build any gate, and hence it covers the whole region. And I'll also count these most important gates. So C-naught is, of course, contained in the region of green since it lies here, and swap is at the top. So I need three I-swaps to build a swap. And finally, I'm going to report this Haar score. The Haar score is our way of determining the expected cost for any gate. The Haar distribution is a uniform distribution over gates in the Weil chamber. And so you can kind of think of this as a weighted average or expected cost for a random unitary. And if we repeat this in principle for all the candidate gates, but these main ones, the I-swap, the C-naught, the B, and their associated fractional components, the square root of each gate, we can reason about each of their expected decomposition costs. And if we were to stop the story here, we know that B, incidentally, is the minimum needed for all gates, only ever needs two applications to go anywhere. So if the story ended here, we would tell our physics experimental friends that you should be calibrating the B gate and do all of your computations with the B gate because you only ever need two. And if you do something else, you'll need more copies of your gate and you'll be losing to noise. However, we know that's not the end of the story because there these different parametrizations of the Hamiltonian, the different ratios between conversion and gain, will drive the system differently. And so we need to understand, is the B gate, although it only needs two, if it's a much slower gate, it might not be as useful as, say, a C naught or an I swap. So the second part of the story is relating back to hardware speed limits. And we first have to do a characterization to understand how the drives of our system combine. So this experiment, we're going to sweep the two frequencies together, the conversion and the gain, and apply this gate between a snail and the qubit. So for each of these points is a gate being performed on our system. And we're using like an ancilla qubit or a witness qubit to measure the snail breakdown. So essentially, if the snail is being driven too hard, we're trying to perform the gate too fast, then the snail will be excited. And the snail with this chaotic breakdown that's not completely understood, but there's a lot of research ongoing understanding snail breakdowns, would excite the qubit. And so we can measure the excitement of this ancilla to create a speed limit that is different for each ratio between conversion and gain. And that is the plot on the left. And if we overlay the gates we're concerned with, the I swap and the B and the C naught, we can see that the farther or the higher their speed limit is, the faster we could perform that gate. And also point out that the axes are different on this. So we could drive conversion to 50 megahertz and gain to only 25 or 20 roughly. And so this was also confirming to us that these types of interactions are different, and we could have a much higher speed limit for just the conversion term. So because the conversion and gain are actually interchangeable, there's these like there's actually three lines that don't appear in this. If you were to, instead of doing B with mostly conversion and 1 part, so 3 parts conversion, 1 part gain, you could do the reverse, 3 parts gain, 1 part conversion, but that would be clearly much slower since the gain term is much less favorable. The reason why, just to give you some insight, is because of all the parametric processes in the module that create the interactions. Depending on how you've built your system, the conversion of the gain terms might be more close to other processes in the system, which is what contributes to their speed limit. So it just ends up where your frequencies end up colliding in space. And so if the conversion is farther away, for example, for the snail, you would have a higher speed limit for that gate. So using this plot, we can get normalized durations. So we have an expected time to complete a gate. So we normalize to I swap just having a time of like a single cycle, and then we can say all the square root components have half the time of their full gates, and we also can see that the C naught and the B are slower than the I swap. And if we take the data from the previous slide, we have these normalized expected duration costs for decomposition, which is I know how many cycles I need to perform the gate, and I know how many expected times I need to apply the gate in order to do decomposition. So while previously we knew B gate was the most efficient at performing decomposition, this analysis was able to help us understand why exactly squared I swap is actually the best gate. And this was nice to see because a lot of literature in recent years had been talking about squared I swap being such a great basis gate and very efficient. But now we had very strong evidence, and we understood completely why we could have a gate with certain decomposition efficiency and certain hardware efficiency and say confidently, this is the gate we should calibrate. Of course, the square root of I swap improves over I swap because we've half the duration. And that makes us wonder, why don't we just continuously take smaller and smaller fractional components of our basis gate? Why don't I take quarter root I swap or eighth root I swap? And this is the question that we'll address next. So it turns out that if we have a fractional basis gate, that I, on average, will need more applications of my basis gate to do decomposition. And intuitively, this works like if I have a single unit of work, if I have a single like unit of work my gate is doing, and it's getting smaller and smaller, I just need to do more copies of that same amount of work, but still maintaining the total duration time of decomposition. The downside is that if that single unit of work, your basis gate, is getting much smaller, the previously negligible component of these circuits, the interleaved 1 qubit gates, starts becoming appreciable as your 2 qubit gate becomes small enough to it's almost the size of your 1 qubit gate. And this becomes a problem because now your smaller fractional gates no longer are preserving the total time of the circuit. They're needing more and more single qubit gates that are now inflating the cost. So for example, if I needed 8 copies of an eighth root of I swap, I really have you have 9 layers of 1-qubit gates. So the idea we had was to recognize that there is, based off of the way that we've built our gates, there are drives on the snails which create the 2-qubit gates, and there are drives on the qubits which create the single qubit gates on them. And so while we're doing a 2-qubit gate, we wondered if we could also drive the qubits at the same time. And the idea would be to sort of push these 1-qubit gates to be the same work that would be on the 1-qubit gates would be happening at the same time as the 2-qubit gates. And this changes our interaction to include these two 1-qubit gate terms with some amplitude that changes with discrete time steps. And this idea had been studied a bit in optimal control theory, but it was considering these single qubit gates to be continuous pulses. And what we don't like about this is that calibrating a single 2-qubit gate is already hard enough. And if we have to calibrate a continuum of gates, this causes more and more problems. So the principle we're trying to invoke is that we can have a 2-qubit gate in just as standard, the 2-qubit gate calibrated by itself. And we have a 2-qubit gate that's calibrated in the presence of additional drives. And so we really just have two basis gates, one that's just the standard one and one where we've added these discrete time step components. So if we visualize the set of new candidate gates from this new family of interactions, we get this very interesting result, which was while previously all of the basis gates we could directly calibrate were only on the flat plane of the Weyl chamber, we've now added some steering to our basis gates, which enables them to go off the plane, or it enables us to calibrate directly gates that were previously inaccessible. And this also will impact our decomposition of gates, because if my basis gates can have some steering to them, we could steer to do more efficiently do the decompositions. So for example, the CNOT gate, we could add steering or add the solutions to the 1-qubit gate drives in order to reduce its cost by steering directly to the CNOT. Or similarly for swap, we can add the steer to remove a layer here. It turns out that for all of the basis gates we studied, squared I-swap actually benefited the least from parallel drive. And this is sort of an interesting remark, was that squared I-swap was already so efficient that while all the other gates we studied found significant benefit from doing parallel drive, squared I-swap was so efficient we could only find a slightly minor improvements, but still enough that it was still the first place candidate. So what we learned was, for example, CNOT has some gates that previously needed 3 copies of CNOT to do decomposition, but adding parallel drive could reduce 3 CNOTs all the way down to 1. The other thing we learned is that the CNOT and the swap are more or less fixed costs of the circuit. So I can reduce the number of gates I need for decomposition for HAR gates, just gates that appear in the Weyl chamber, but in like say the middle of the Weyl chamber, but the CNOT and the swap are kind of special points. And so all we can eliminate for these 2 gates end up being the 1-qubit gates in the middle. Those are the ones we push into the 2-qubit gate. And so the results of this paper, which you can find online, are that we recently presented at ISCA, is we use this principle over benchmarks and we're able to reduce circuit duration and boost fidelity, some appreciable amount. And so this was a very neat idea. So the main idea I want to highlight is that we were able to study the hardware in order to confidently say what basis gate is the best, which would be squared I-swap. But then we wanted to try to do something to improve it. And in this case, it was parallel drive. However, parallel drive is somewhat of an intrusive modification to the calibration scheme for experimentalists. We are telling them they have to engineer a new Hamiltonian and calibrate different things. And so they might kind of shrug and say, it's not worth it because it will be so much effort to build it. So depending on the system and your speed limits and your basis gate and your circuits you're trying to decompose, you could find huge advantages to parallel drive, but there is an even simpler way that you might improve the squared I-swap gate without having to make such an intrusive modification. And so this will be our more recent work, which is studying the concept of mirror gates. So that's what I'm going to introduce now. The idea is of a mirror
question
gate.
for the previous.
Oh yeah, go ahead.
A small question when you evaluate the circuit duration and fidelity, do you use the real hardware or the simulation results?
Yeah, it's a good question. It's all simulated mainly because we're interested for our research for like larger scale considerations. Like in our research lab, we are studying like smaller components of how do we make very efficient couplings, how do we make efficient qubits. and how can we like make those so that they're robust to scaling. So we don't have a large enough system to say benchmark hundreds of qubits, but we're trying to design methodologies that would be robust to them. So that's why we end up doing simulations, is so I basically so I can test larger circuits that would be possible on our system currently.
Okay, yeah, that makes sense.
Yeah, so the fidelities are all just simulated with a basic model of decoherence over time.
Gotcha.
Okay, so parallel drive was our method of saying squared ISWAP is the best gate, but decomposition for two qubit gates is more or less a fully solved problem. So like we don't want to just end the story there. Like what else could we possibly do to make a squared ISWAP gate better at transpiling? And the idea that we started with was that for these all-to-all neighborhoods that are local in our module, the four qubits coupled to a snail, you might not care about the order of where your qubits lie because I already have all-to-all everywhere within these four. So that gives me a lot of flexibility with how I might choose to decompose my circuit. So if I have some CNOT and I have maybe like adding a swap gate here, you can think that I just use these, I can just rearrange the order of my qubits and I could just keep doing free data movement and build different gates. However, I left this up for a while. Maybe some of you are frowning at this. This is actually not true. And I wanted to include this cartoon because this is something that confused me. Despite me mathematically knowing that this wasn't true, sometimes you look at the swap gate and you just intuitively think, okay, I'm moving things around, I'm just flipping the wires, so my CNOT that I have played is just an upside down CNOT. And I knew this wasn't true, but I often looked at this circuit and I didn't always recognize it immediately. So what actually is true is that the CNOT is flipped upside down by these Hadamard gates, but it makes me wonder, like, what is the CNOT and a swap? So this is what we call a mirror gate, where you have some gate and you have a swap after it. You can say that that's the mirror of the gate. So a CNOT and a swap would be its mirror. And sometimes you might have seen this in the research, some research papers, they write the swap with three CNOTs, and then the two first CNOTs of the circuit will cancel. So sometimes this mirror gate will look like a CNOT followed by an upside down CNOT. That's creating a mirror of a CNOT. So this is an interesting gate that we wanted to study because in our all-to-all modules, the idea of routing and translation are no longer independent. For each swap, we also have to decompose the swap. So we should kind of concern ourselves with both these at the same time. But also, we might use the idea of the flexible routing in order to influence how we do basis translation. And so now we are kind of like bridging routing and translation to happen at the same time. So let's revisit the monodromy polytope coverage sets. But now I'm going to include for each of these gates the mirror polytope. So I can construct these in two different ways. Either I take the polytope and I take every point inside of the polytope and I compute its mirror coordinate, which I'll have an explicit equation on the next slide. Or what you could do is, since the mirror is created just by having a swap gate, is I can tell monodromy that my basis set includes a free swap gate. So this would just be like arbitrarily relabeling the virtual to physical indexes of my qubits. I have a no-cost swap, and it will compute the possible circuits I could build, and I'll have the possible circuits just traditionally will build my polytope I'm familiar with, but I can just append a swap, and for the same cost, it will overlay its mirror polytope, which is how we create these regions. So we know that identity mirrors to swap, and this is intuitive because if we have nothing and we just add a swap gate, all we're left with is just the swap. So you might think that we have some gate and it will translate itself here. But I also see that this bottom plane is like vertically flipping. So I have this horizontal plane and I have a vertical plane. And so this is sort of an interesting it's an interesting change of our coverage sets that we wanted to understand. For these other gates, because the identity and swap are its mirrors, when our coverages start in identity, now they have this disjointed set that's more obvious, like working down from swap into the middle of the wall chamber. So the way you should think about this is that if I don't care about the ordering of my qubits, for example, in an all-to-all topology, I now have an effective higher volume coverage of the Weil chamber because I could decompose a gate for k equals 2 applications of my basis gate, if it was in, say, this region, or if it was in this region, which was different from before. So I have, in in effect, a lowered expected cost of decomposition by enabling this freedom. I'll also point out that these are like 3D volumes that are more obvious to see in software when I can pan around. So this is actually a pretty large volume of the wild chamber. And it leads us to ask, when you add these mirror volumes, how much does it improve your hash score, which is the next thing I'll show you. So we're going to answer how much it improves the hash score, but we're going to add one more thing, which is approximate decomposition. Approximate decomposition is this fantastic idea that because the gates that you're doing decomposition with are themselves noisy, in order to have the highest fidelity decomposition, you might choose to do an imperfect decomposition in order to boost the overall fidelity. So for example, if I needed to decompose something with 3 CNOTs, and each of my 3 CNOTs is going to give me some loss, each sends some loss because my CNOTs take time, I might instead do only 2 CNOTs and get a pretty close decomposition, but overall much higher because I didn't have to have a source of noise from that 3rd CNOT that would normally appear. And I really like this idea that was presented at March Reading this year, which is intuitively, the way you think of this is that if I'm allowing some approximation, you're inflating your coverages because I'm now having some wiggle room of something that's in my acceptable threshold of decomposition. So if it's close, but not quite contained, depending on how much approximation I'm enabling, I will inflate it and say, now it's covered by my approximate region. So the idea is we have exact decomposition with this picture on the left. We have mirror decomposition where we added this polytope of the mirror of the original polytope. But for each of these, we could also allow approximate where we've added some layer above it, some inflated version of the volume. And for each of these 4, we can compute the hash score. And what we do is an experiment that looks like this. I will just sample a random point in the wild chamber, and we'll use our numerical decomposition optimizer tools, which basically treat the circuit as a variational quantum circuit and optimize over the free parameters. And then if that optimizer converges, we know that a solution to the decomposition existed, and if it doesn't, we say it failed. And if it failed, then we would increase K, we would add another iteration of my basis gate, and I would go to the next version of coverage and then test again, does it converge? And when we do this for in a Monte Carlo simulation, we find that the square root I swap and quarter root I swap, the ones I'm presenting here, do as we expect. The exact score gets improved by allowing approximations, which again gets improved by allowing mirrors, and again gets improved by applying approximations and mirrors. The square root I swap kind of converges at 1. This is kind of the lower bound that's possible to do with a single gate. But quarter root I swap was continuously being improved. And so similarly to parallel drive, where we recognize that there's sort of a threshold for how small your fractional gates be, we kind of concluded quarter root I swap would be, you wouldn't want to go much smaller, at least in the near term. And for the similar experiment, we concluded quarter root I swap is just better than square root I swap. You can get a little bit more bang for your buck without kind of going crazy off the deep end. Very small fractional basis gates might give you a problem. I'll also point out that an interesting part of approximate decomposition is that for CNOT specifically, this region is technically 0 volume because they're all planes. So the CNOT has a hash score of 3 because in order to have any non-negligible volume, you need to have 3 CNOTs, and this is only 2. But the mirror polytope, although it didn't add any volume, it would decrease the average distance to the polytope, which means that CNOT mirroring doesn't improve the hash score, but CNOT mirroring and approximations does improve the hash score because the additional non-zero plane would decrease your distance. I now have access to a closer region of the polytope I could approximate into. So we use this idea, we lower the hash score, we lower expected decomposition, we can calculate some expected decrease in fidelity, which was a nice result to see. So from mirroring, I presented this first idea, which was the mirroring gives us an effective increase of decomposition. But the other part of this is wondering if we can more strategically use the idea of a mirror for something on purpose. We have this swap built into this identity, and it makes us wonder if we can force the swap to appear and can we do data movement with it in a strategic way? So the key idea that we recognize that is quite powerful is that for decomposition specifically into the squared iswap basis, the C naught can be decomposed into two squared iswaps, and ultimately the identity of the C naught in the mirror is locally equivalent to an iswap, which is trivially itself two squared iswaps. I should point out that we are not the first people to identify that this sort of circuit can be taken advantage of, but in the literature, these were all disjointed projects. For example, in the paper itself, this preprint, I point out maybe like 8 or more papers that independently found circuits like QFT, QAOA, certain entangling ansatzes, etc., that showed that you could decompose these with an iswap to get some advantage. But they were missing the second component, which is that for no additional change, you could also decompose it into two squared iswaps. So very crucially is that we now can recognize that there is an equivalent cost between a C naught and the C naught mirror into the squared iswap basis. And what we wanted to do is generalize all of these results that say this identity exists, but say that this is really something that can just be baked into the transpiler. And instead of discovering these by hand independently, if this was just something that existed in the transpiler, all of these would decompose most efficiently, taking advantage of the mirrors when most appropriate. I'll also point out something interesting, which is that the parallel drive work enabled us to change the C naught decomposition by removing one set of interleaved 1-qubit gates. But in a very different way, adding the mirror of a C naught also removes one layer of 1-qubit gates, because if you decompose this iswap into two squared iswaps, there would be no 1-qubit gate between them. You would just apply the squared iswap twice. So those are two different ways that you can use parallel drive or mirrors into the squared iswap basis to improve the decomposition of C naught. Okay, so why does this work, and what are we going to do with it? We have C naught and we have a mirror of C naught, but more generally, all of the gates have mirrors, which can be explicitly described by an equation over the coordinates like this. And for this figure, I'm showing for different basis gates what the mirror looks like. So identity, this dark blue mirrors to swap, and along the C naught is this linear relationship, so where all of the C phase gates map to the P swap gates, this vertical line in the Weyl chamber. And eventually, the light blue, the C naught, we see mirrors into the iswap. And this makes sense given the equation of the identity we saw on the last slide. But why it works is because this black outline is the two squared iswap coverage region. And this is the only gate that is contained by k equals 2 squared iswap. So in the squared iswap basis, I could decompose all of these gates with 2, but only the iswap with 2. And the only gate that appears twice is this gate. So it's a very special property that exists for C naught and squared iswap. Sorry, C naught and iswap, that both of them have equivalent costs. And we don't have to add any additional concerns. We can just say, should we accept one or should we accept the other? And we know it won't modify the cost of the circuit. This plot also helps us understand this that appeared earlier, which is that the C phase gates that appeared in my benchmarks from, for example, the QFT circuits were sometimes being mirrored purely by accident by Qiskit, because sometimes Qiskit might put a swap after C naught, and it creates its mirror of the P swap gate. Although this gate didn't originally appear in the circuit, it's something that can sometimes fall out naturally from the transpiler. But our goal is to kind of tell the transpiler to more intentionally take advantage of this instead of just sometimes accidentally putting a swap next to a C naught. So that's the idea, is to use the mirroring for data movement. The idea is that because these two circuits are identical in costs, all we need to consider is that for a C naught in my circuit, should I play the original circuit C naught, or should I play the mirror of the C naught? Should I transpile into a version of the C naught that inverts my qubit outputs? So if I wanted to do that, I would just substitute the identity on either the left or the right. And if I do the one on the right, I've now done a baked-in swap. The swap is now just baked into the decomposition. So the language that might help by distinguishing these is swaps that are themselves actual swaps in the gate are explicit swap gates, but this is sort of a virtual swap gate because it's doing the data movement of a swap, but it's virtual in the sense that there is no swap in your circuit. It's baked into the decomposition itself. So if I wanted to decompose or transpile this full entanglement circuit to a line topology, we'd recognize that these gates can't be mapped because they don't have edges, assuming that we're linearly connected just vertically between 1 and 3. So if I gave this to Qiskit, it would induce these swaps where appropriate. If I don't have a gate that's mapped already, I just pick a swap in order to make the topological distance of the gates that haven't appeared yet minimized. And eventually, if I put enough swaps in my circuit, I'll have all of my gates routed and executable, and we'll get some final circuit. So this is what the highest level of Qiskit optimization gives me. And I'm counting the cycles of ISWAP times. So CNOTs will count for 2 squared ISWAPs and swaps will count for 3. And this gives us a total depth cost of 16. But if we were to more intentionally place our swap gates, we can get a different circuit, which looks like this, where now all of the gates that appear in the middle of the circuit, instead of having any explicit swap gates, we have no explicit swap gates. And all of the swaps, all the data movement can purely be done by using the ISWAP gates or using the mirrors of the CNOTs. And this gives us a total depth of 10. So a fairly significant reduction of depth. And all we had to do was no changes to anything other than just recognizing that this decomposition and the routing problem were independent. And I point this out because in the way that Qiskit's transpiler is built is that these two concerns are very independent. They're built as separate stages. So if I do routing, this is performed entirely before I translate. And this is key because it means that I can't recognize that certain routing choices will decompose more efficiently. And the way that we are able to do it is by using the monodromy polytopes. And it means that we don't have to do pass 5 here, translate to the basis gates, in order to recognize that we have decomposition costs, but we don't actually have to do the decomposition. So we can still put the decomposition to happen later, but I can reason about the expected decomposition costs at pass 4. And that's what we're going to build into the transpiler modification of Sabre. Sabre is the algorithm that exists in Qiskit that does their highest level optimization swap routing. The way it works is it takes the representation of the circuit as a DAG where all of your gates are nodes, and will take gates that have all of their predecessor resolved. So in the circuit, gates that don't have any gates before it are going to appear earlier in the DAG, and those move into the front layer, which is just a stack that exists in the algorithm. And if it's executable on our hardware, it means that the topology has an edge and it's already been routed. It moves to the execute layer. If we can't play any gates in our circuit, we're kind of stuck because there are no edges, then Sabre will invoke some algorithm that finds the cheapest swap gate, and it will repeat and keep removing gates, resolving their dependencies, finding them edge to compute on until the whole thing is mapped. But we're adding a new layer, the intermediate layer, that takes every gate that leaves the execute layer and now considers whether or not we should use the mirror of that gate. The idea is simply, since these don't change the decomposition costs, all we have to ask ourselves is, does this improve the topological cost, which is the same cost function that the insert best swap subroutine uses? Is it a swap that will make me does it move gates that need to play in the future closer together? And if it does that, then this is something that will resolve swaps without actually having to do the explicit swaps in our circuit. And this is great because by building it into the algorithm like this, we don't have to modify any concerns of say like look ahead or non-immediate gates in our circuit. We can just use a very straightforward cost function and say, do the mirror gates, do something efficient in our circuit, and will they help me with routing? Will I be able to reduce the swaps I need in my circuit? And this works quite well. So here I show some of the results we computed where I ran Mirage, the name of this new algorithm, in contrast to Sabre, over a set of circuit benchmarks. And we can find that it does quite well on the heavy hex topology. The heavy hex, as I've talked about earlier, needs a lot of swap gates. And so adding the consideration of mirrors purely at a software level will significantly reduce the depth and total gate count of the circuit. And so this was a great and exciting result to see. If you're interested in this, I've built it to be a Qiskit transpiler plugin, which means that to take advantage of transpiling with Mirage, all you have to do is install the package, and it works natively with the Qiskit transpiler function. By pip installing my package, it gives you access to these routing methods, barrage, and my layout method. The rest of the paper that you can find in the preprint, we go into some more considerations, for example, the post-selection criteria for multiple trials over Sabre or Mirage that have happened in parallel. Mirage is able to consider the one that minimizes depth, again, by taking advantage of decomposition costs without actually doing decomposition, whereas Sabre can only count number of swap gates, and this gives us some bonus. We also talk about some variable acceptance thresholds, so that green box considering mirror gates, there's different thresholds you might accept in order to vary your degree of success for different types of input circuits. And finally, some speedups related to coordinate caching built into the unitary class and a faster block consolidation, which is like input cleaning before you run the Mirage. And this can all be found online. So in conclusion, we talked about our co-design methodology that enabled us to reason about the hardware to determine the most efficient basis gate. But then we went a step further and said, how could we understand the hardware and the transpiler in order to boost the efficiency of that squared ISWAP gate even further? And we introduced the parallel drive, which could reduce circuit duration. And in contrast, we introduced the mirror gates, which bridge the ideas of decomposition and routing to further improve fidelity related to approximate decomposition for our all-tall neighborhoods, and as well to reduce depth from integrating data movement into the decompositions and removing explicit swap gates. And this will altogether give us a really neat way to improve circuit fidelity. So yeah, I want to say thank you to everyone I worked with. If you're interested, connect with me online. I'd love to talk more about any of the research we're doing, or if you're interested in our labs. And yeah, thank you all for listening.